So students, let's start off with the Miley for forced vibration. Yesterday we have seen that what is forced vibration. We have defined forced vibration as externally applied periodic force with frequency different from the natural frequency of vibration to let the system continue sustained vibration, isn't it? So, and we have discussed it in using an electrical oscillator with its sinusoidal voltage and current, such that we can write the voltage equation in this manner, and then substituting the value for current E0 e to the power I omega t, what we obtain, as you have seen for VL, this is what we get, isn't it? For VC, this is what we get. The component of I which is multiplied shows that voltage leads current by 90 degree, and minus I tells that VL over here leads current by 90 degrees because of positive I, and VC lags current by 90 degrees because of negative I. So this was what we had observed. I had started off my forced vibration with the observation of these things, okay, and we have seen that, well, this was what we had observed yesterday, that that you can write down the total voltage. The voltage for resistance is VR equal to IR with no I term, so it is same as that of the current. It doesn't lead or lag, okay, so that the total voltage comes out to be this, and from there we could generate this vector diagram, okay, with we have the reactance for inductance, reactance for capacitance, and the corresponding resistance. Together it gives us the impedance, which is given in this manner, the resultant, making an angle phi with the resistance. So the inductance, the magnitude is given by this, the phase angle is given by this. We have seen omega L minus 1 by omega C by R, and well, when omega C is equal to 1, omega L is equal to 1 by omega C, we have observed that the impedance is minimum, ZC is equal to R. Now mapping this to a mechanical oscillator of mass M, stiffness S, and damping constant R, when subjected to an external periodic force given by this is what we have in the equation. This is equal to 0 when it is a damped oscillator, and as I repeat, we require sustained oscillation and no sustained damping such that the system goes down to 0, for which we apply this periodic force, okay, and this keeps the system oscillating. So the differential equation of damped oscillator changes by only this amount. Instead of 0, we have the externally applied periodic force, and the solution we write in this manner. When we substitute the solution, observe that the solution has an I factor, a cosine factor, because we knowingly apply an external periodic force. Why? To maintain periodicity in the system. So the solution will be periodic, and therefore we take it as A e to the power I omega t. And you see over here that dy dt is given by this. And if we proceed with the solution, which you must be having in your copy or you must be having in your system, then this is what we get for impedance, okay, which is force per unit velocity, okay. So you see that is the mechanical impedance here. Now when we try to sort of draw a vector diagram of the same, you see this is now Im omega, this is minus Is by omega, this is Zm, and well, the same differential equation if we proceed with, this is what we get for our amplitude. So what we try to do over here, we try to make it simple. We try to get an ultimate form for the amplitude, because we have seen that the amplitude for free vibration is fixed, it doesn't change, but the amplitude of damped vibration changes, because of which we have to study log decrement, relaxation time, quality factor. And so now we want to see that after applying an external periodic force, what happens to the amplitude? How does it look like? So this is the amplitude that we are getting over here, where we put Zm, the impedance, well, in this form. The vector form of Zm is given over here. If we put r equal to z cos phi and this equal to z sin phi, then you see your Zm can be written as in this manner. Zm, see, because this is r plus I omega m minus s omega m. So you have it in this manner. Therefore, you write it like this, and this is nothing but Zm e to the power I phi. The modulus of Zm being this, what we have over here. Okay, square root of r square plus omega m minus s by omega whole square. Tan of phi is omega m minus s by omega by r. Okay, so why the displacement, ultimately the solution to the forced vibrator, which we have taken as a e to the power I omega t, okay, that is actually equal to I f naught. You get this as the solution. So, but you know that your externally applied periodic force over there is f naught e to the power I omega t. So here you see this is your amplitude now. You get this as your amplitude. So now in today's class we will start our discussion from